This is the second video on section 12.4, which is about cross product. And let's briefly remember the concept. Given two vectors in R3, say vector A and vector B, the cross product is computed in this way. That's how we did in the previous video. And then A cross B is a vector. But what kind of vector is that? Well, pictorially, if you have vector A and vector B like this, and then vector A cross B is a vector perpendicular to both A and B, but the precise direction of the cross product is given by right-hand rule. And if you switch A and B, and if you compute B cross A, the vector, the cross product, points to the opposite direction. Okay, so that's what their cross product was. Then now, today, let's do this example first. Example. Let A be 1, 3, 2. Then now, let's compute A cross A, namely the cross product of a vector A with A itself. And let's see what we get. This is, so A cross A is by using this one. You put I, J, K, and then you list the entries, you list the components of the vectors like this. And since we are computing cross product of A with itself, we just list the same numbers like this. Then now the way to compute it was pick up I and then hide those. And then what you're left with is 3, 2, 3, 2. And similarly, the next term is negative J, and then hide those. And I get 1, 2, 1, 2. And then finally, plus K, K, and hide those. And what you're left with is 1, 3, 1, 3. Okay. Then now, just to make sure, the important thing is that the middle guy gets negative sign. So signs alternate, plus, minus, plus. Then now, let's work this out. So to compute this, you do like this, AD minus BC, so to speak. So this is 6 minus 6, I, minus 2 minus 2, J, plus 3 minus 3, K. And then this is 0I minus 0J plus 0K. What's this? Well, this is just a zero vector, 0, 0, 0. 0, 0, 0. Another name for this is the zero vector. And this is not a coincidence. And indeed, in general, if you compute the cross product of a vector with itself, you always get a zero vector. So in general, A cross A is always 0. Okay, then now, this is actually a special instance of some other property of a cross product. Namely, for cross product, like I said, if you have vector A and B, and if you compute the cross product, you get the vector perpendicular to both A and B. Then now, how about the magnitude of cross product, the length of cross product? Well, it turns out that the length of the cross product is written in this way. So here's a theorem. Let theta be the angle between A and B. Then the magnitude of A cross B, magnitude of the cross product, is written as the magnitude of A times the magnitude of B sine theta. Actually, we have seen something similar before. Let's recall. A dot B was the magnitude of A, magnitude of B, and cosine theta. So it looks similar, but not the same. All right, but well, let me just put it here. Then now, but what is this geometrically? Well, let's write down this picture. Vector A and vector B. Okay, and then theta is the angle between A and B, so it's theta is here. Then the magnitude of A is, of course, the length of this line segment. And the magnitude of B is the length of this line segment. This is the magnitude of B. Then, what's this? B sine theta? Well, this is pretty much by definition of sine theta. It's just a height here. Namely, if you write down the parallelogram like this, doesn't look like it, then this height here, height of this parallelogram, is the magnitude of B sine theta. Right. And then if you multiply A and B sine theta, which is the height of the parallelogram, and then magnitude of A is the length of the base, then what you get is, of course, the area of the parallelogram spanned by A and B, so to speak. So the area of this, of the parallelogram, so to speak, spanned by A and B. This is precisely the area, well, I mean, not the area, this quantity, sine theta, and that is precisely the magnitude of the cross product. So more pictorially, here's what's happening for cross product. You have vector A in R3, and you have another vector B like this. And the cross product is perpendicular to both, and the precise direction is determined by the right-hand rule. So this is A cross B. Then now, here we have the parallelogram spanned by those two vectors, and the area is the length of this cross product. Area is precisely the magnitude of A cross B. So that's what's happening for cross product. Okay. So therefore, if A and B are parallel to each other, namely if the theta, the angle theta is 0, or maybe 180 degrees, namely suppose you have your A is like this, and your B happens to be like this, or maybe like this, then of course there is no parallelogram, there is no area. Basically the parallelogram gets collapsed, so to speak. So in that case, sine theta is 0. That means the area is 0. So therefore, the cross product has magnitude 0, which means the 0 vector. Namely, here's a little theorem. Two vectors A and B are parallel to each other, if and only if the cross product is 0. But 0 means 0 vector, so it's a 0 vector. So pictorially, either you have a situation like this, A and B. In this case, theta is 0 or 0 degrees, or A is like this and B is like this. In that case, theta is 180 degrees. Either case, you don't have the parallelogram spanned by dots, which means the area is 0, which means the cross product is 0. Okay, then now, using this property of cross product, we can do this kind of exercise. So here's an example. Find the area of the triangle with vertices P 1, 2, 1, Q -1, 0, 1, and R -1, -2, 1, 3. Okay, let's think about this problem. Okay. So how are we going to do this? Here's the answer. Suppose that our P is here, and Q is here, and then R is here. So this is a triangle PQR. Then we want to find the area of this triangle. And now, let's call it the vector PQ, A, and then the vector PR, B. Then we know that the magnitude of the cross product of A and B is the area of the parallelogram spanned by those. So that means if we somehow compute A cross B and then compute the magnitude, that gives you the area of this parallelogram. So therefore, the area of the triangle is just half of it. Namely, let vector AB PQ, the vector from P to Q, displacement vector from P to Q, so to speak, and B PR. Then the area of the triangle PQR is half of the magnitude of the cross product. So all we have to do is first compute explicitly in terms of components those two vectors, and then just compute the cross product and compute the magnitude. But how are we going to compute the components of vector PQ? That's vector PQ. This one is what? Well, here's a way to do it. So this is P, this is Q, and we know the coordinates of P and Q as those. Coordinates are those. What does that mean? That means the coordinates give you the components of the position vector, but position vector is a vector coming out of the origin. So our origin is somewhere here. And then we know what this vector is, and we know what this vector is too. Namely, the components are given by the coordinates of those 2 points. And then by looking at this picture, what is the vector PQ? Where that is, you start from P, and then you have to go to Q. So that means if you reverse the vector OP to PO, and then go to this way, and if you add those, what you get is the vector PQ. So therefore, vector PQ is computed as OQ minus OP. But what's OQ? Well, OQ corresponds to just the coordinates for the point Q. So it's this, and then minus the other one is this one. And then this is computed as -2, -2, 0. So after all, what we do here is just subtract coordinates of the starting point from the coordinates of the ending point. And then that's how you get the components of the vector PQ. And then we can do the same thing with PR. So vector B, which is PR, that is OR minus OP, and that is, in this case, R is what? -1, -2, 1, 3, minus 1, 2, 1. And then you will see that this is equal to -3, -1, 2. Yes. Okay, so we got those 2 vectors for vector A and vector B. Then, like I said, we have to compute the cross product of those 2. So A cross B, that is I, J, K, -2, -2, 0, -3, -1, 2, and then compute the determinant cross product, and this is equal to I times, you just do like this, and then you get -2, 0, -1, 2, and then J, and you hide those, -2, 0, -3, 2, and then K, and you get -2, -2, -3, -1. And then if you do like AD minus BC, so to speak, multiply diagonally and subtract, you get -4I plus 4J plus 1 minus actually 4K. Or if you prefer this bracket notation instead of IJK notation, it's -4, 4, -4. Okay, so therefore, the magnitude of the cross product is just take the squares of all those, add them, and take the square root. And take the square root, and you will see that this is 4 root 3. 4 root 3. And therefore, the area of the triangle is half of it. Magnitude of the cross product gives you the area of the parallelogram. And if you want to get the area of the triangle, you have to divide by 2. So therefore, the area of the triangle PQR is 1/2 times 4 root 3. That's 2 root 3. Okay, so that's one sort of application of one geometric application of cross product. Okay. Then now, as the last thing in this section, let me list some of the properties of cross product, more like some sort of algebraic properties of cross product. Properties of cross product. So let A, B, C be vectors in R3. So once again, just to make sure, a cross product exists only for R3. There is no cross product for vectors in R2. And alpha, a scalar, a number. Then, property number 1, which we have already seen actually, A cross B is negative B cross A. So if you change the order of multiplication, you flip the direction, you flip the vector. Now, alpha A cross B. This is equal to alpha times A cross B. And then that is the same as A cross alpha B. What this means is you multiply alpha to A, namely you extend the vector A by alpha, and then take the cross product with B. That's the same as taking the cross product first and extend the cross product by alpha. Or you extend the vector by beta, vector B by alpha, not beta, I'm sorry. Extend the vector B by alpha and then take the cross product with A. So those three coincides. 3, A cross B plus C. And this is A cross B plus A cross C. Namely, you can distribute cross product like this. Or in other words, suppose you have 3 vectors and you add B and C and take the cross product. That's the same as taking cross products first and add them. Okay, then now, of course, you can do the same thing from the other direction. So here, A plus B cross C, and that's the same as A cross C plus B cross C. You can distribute from this side as well. All right, and then now, number 5, there is something called a triple product. A dot B cross C. Okay, this means you take the cross product B and C, and then you get the vector, and then take the dot product with A. Okay, somehow surprisingly, that's the same as A cross B dot C. Somehow you can flip dot and cross product here. And then this is called a triple product. This formula is called a triple product. Finally, property number 6, A cross B cross C. What's this? Well, unfortunately, this is not equal to A cross B cross C. Unfortunately, this is not the case, but this is actually equal to A dot C times B minus A dot B times C. So remember, dot product is a scalar. Cross product is a vector, dot product is a number, scalar. So this is just a number, and you just multiply this number to the vector B, and minus, you get this number, and you just multiply the number to the vector c. Looks a little weird, but that's true. And the verification is your exercise. So it's a good exercise for you to verify it. So verification is your exercise. Okay. So you can just pick up some vectors ABC. You just randomly write down ABC, and just verify, for example, this. You just compute cross product and take the cross product, and then you can actually verify yourself that that is equal to this. And the other things too, all the other properties you can just verify. Okay, so that's all I have to say about this section 12.4 on cross product.